Can you hear me? Hello, everybody. Okay, thank you. Welcome, everybody, to this experimental testing for aerospace structures class. Today, we are going to see some last details about the structural updating method that is called predictor corrector that we start using just yesterday. And then we will see some other estimating techniques that are very fancy and very useful in specific conditions, structural conditions. So let's dig in with the structural updating method called predictor corrector. Just to remind you what we did yesterday, we introduced two correlation functions, namely chi-s and chi-a, that are correlating the frequency response function. So instead of using, for example, the MAP matrix, the MAP value, sorry, that is the model assurance criterion, or the MSF, or other tools that are relating the model properties, numerical and experimental model properties. In this method, what we are doing is just correlating the response model through the frequency response function. So the chi-s and the chi-a functions are functions in the frequency defined in the frequency domain, and they are correlating the experimental and numerical frequency response function in the way that we are having written here. The basic things of these correlation functions, because of their definitions, are functions that are all defined in a 0-1 range. 0 means that there is no correlation at all. 1 means that there is a perfect correlation. Okay. And the second step in this predictor corrector method is to introduce the design parameters for structural updating using the so-called p-value formulation. That is, we are entering into the elemental matrices of your final Kalman models, both K and N, that is both the stiffness and the mass matrix, and we are introducing those design parameters as some parameters that are multiplying these elemental matrices, K or N. Those parameters are cast together in order to build your this structure updating design vector P that contains these parameters. Please note that not always we need all these parameters. That is, maybe sometimes we feel that the structure updating could be obtained just by looking at the stiffness matrix only, or at the mass matrix only. Rarely what we are doing is to consider both of these parameters. But however, in order to have the formulation in a more complete form, we are introducing all of these parameters. Also, there is not the need sometimes of having all these parameters that are related to the number of elements, Maybe what we need is just a few parameters that are linked to some elements and not all the elements. Okay, so the dimension of these p vector, that is the vector of the structure parameters for updating, could be of dimensions that are much lower, much less than the number of element twice, generally speaking. Then, by taking the derivatives of the previously defined correlation function of the frequency response function, and by defining a residual vector that is your vector epsilon, then we have to solve for the change of these design parameters for updating delta p, okay, by solving this equation. Yesterday we saw some details on these elements. What we can say is that the elements ij of the sensitivity matrix, that is the name of the S matrix, are the ones that are given there. And of course, because we are having two correlation functions, that is chi S and chi A, and we have to consider that the rows could be different according to the row index, as I said, as I wrote here. Okay, from this point of view, we can say that these coefficients, the derivative of the shape function with respect to whatever parameters, okay, could be viewed as a prediction of your solution in terms of change of the design parameters for updating, and the derivative chi a with respect to the pj, okay, could be viewed as a correction, okay, of the solution. Thus, there is the name of predictor corrector method. Okay, so just to give you the reason why this method has such a name. Now, if you look to the general solution, as you can see, what we are having generally, as I already talked about that, what we are having is that the number of frequency line is generally much larger than the number of design parameters, okay, that we have to consider, okay, and is the number of design parameters for updating, okay, there should be less or equal to the number of the twice the number of elements, of course. In general, what we are having is that this number of design parameter is much lower than the number of frequency line, and therefore we have to go to look for the solution in a least square sense. Okay, so least square solution scheme is generally adopt to solve for the change of such parameters, such design parameters, okay? And specifically after a number of tries and after a number of evaluation from both the numerical efficiency point of view and from the accuracy point of view, the Bayesian estimator technique is proved to be best in solving such a kind of problem. So what we can write here is that the Bayesian estimator technique is giving the more accurate results by experience. Okay, so that is, if you want, the key point from this numerical solution techniques point of view that one has to consider before trying to solve this approach. And in order to introduce this Bayesian solution technique, what we can say is that if there are some rows, okay, that are characterized by a higher accuracy than others, okay, then maybe we can introduce some weighting matrices in order to give more importance to such rows, okay? So if some rows which correspond frequencies, okay, your sensitivity matrix, so frequency lines in the sensitivity matrix. So if some rows are more, let's say, accurate with respect to other lines, okay, then maybe some two weighting matrices are considered, okay, to help the solution process. These weighting matrices could be viewed as the matrix CR, okay, and the matrix CP, okay. This matrix R is taking into account for the residual term, okay, that is taking into account the vector epsilon, whereas the CP matrix takes into account for the possible solution vector P. Okay, there are different formulations for such a matrices, but maybe it could be straight for you to just consider that if you use the correlation function chi A and chi F, maybe they could be used as components of such a weighting matrices. Okay, so if we are introducing such a formulation, such a weighting matrices, by the Bayesian estimator techniques could be followed just by minimizing the functional, let me write it as calligraphic F, defined as your residual terms times this weighting matrix for residual times the residual term, okay, plus delta P transpose Cp delta P, okay, and the solution is given by this equation. So the change of the design parameters for updating could be viewed as your sensitivity matrix P transpose CR sensitivity matrix P, oops, plus CP is to the minus 1. And then what we got, everything times S P C R epsilon. Okay, and that is your very interesting equation that is solving you the problem for structure update. Please note that SP is the sensitivity matrix refer to the active parameters P. Okay, PI. Sorry. What does it mean? That it means that in this approach we can define an alternative scheme that is allowing you to iteration by iteration to have the change of the design parameters, introduce those design parameters, new values of the design parameter into your numerical model, evaluate the new response function, that is the new FRF, and then recompute the correlation function and start again with the procedure until the change of the design parameters are not that important. You can refer, for example, to the amplitude of your vector, or the maximum change in one design parameter should not be larger than a square code. Okay, this iterative procedure is needed to go to convergence, just because the relation between your change of the design parameters and your correlation function chi A and chi S are non-linear. And therefore, because we linearize the process, remember we consider a first order approximation, then when defining the sensitivity matrix, then we have to introduce such an iterative procedure. Okay, so because the relationship between your change of design parameter and the correlation function chi A and chi S, sorry, chi S of omega is not linear, and because S is defined in a linearized equation, and iterative process is introduced to solve for the design change of the parameters for updating. Okay, so if now K is the kth iteration step, then your design, the vector of design parameter at the next iteration step is equal to the value of your design parameter at the actual k iteration step plus your change of the design parameter that you got here at the ith iteration step. And then iteration stops when, for example, the amplitude of the vector, the difference between the value of the design parameter vector at the iteration step k plus 1 with respect to what we got at the iteration step k is less than a prescribed quantity, less than a tolerance that is a small arbitrary quantity that is defined by you, given tolerance, okay? Okay. Now, just a few remarks on these predictor corrector methods. So, some remarks. So, what we got here, we already discussed that. First, the number of frequency lines are generally much larger than the number of design parameters that we consider for the structure updating, okay? Number of design parameters for the updating. Okay, and because of this, they introduce some numerical instability. Okay, and moreover, because this information is much larger than the information required to solve the problem, the number of rows, if you want, is much larger than the number of columns. Okay, some some rows, if you want some equation, may introduce noise or dummy information that, however, contributes to the instability of your numerical approach. Okay, as a result, the solution techniques consider that rows having pure correlation are neglected. Okay, and we can do that just because we have many rows available. Okay, so your correlation function chi A, chi S are also used to remove some, let's say, additional unwanted information because of noise or because they are meaningless. Okay, then another point. Okay, rows with excellent, so just the opposite, correlation are neglected too. Okay, this in order to increase the numerical efficiency, okay, of the algorithm that we consider. Okay, so not only we are removing rows characterized by very pure correlation, but also those rows that are characterized by the very by the maximum correlation that is close to the unitary value, just because not to have dummy information, okay, because we can't say much more about that. Okay, we want to improve the efficiency, numerical efficiency, by removing that. Moreover, as you well know, when we are considering your frequency response function and we are across the natural frequency, by small changes of your running frequency across the natural frequency, we are having large variation of the frequency response function, just because we are across the peak of resonance. So very small variation in the x-axis correspond to a large variation in the y-axis. Okay, and therefore this could also reduce the efficiency. This could also introduce some numerical instabilities in your iteration process, and therefore rows across the peak of resonance are also neglected, okay, to reduce, once again, numerical instability. And that's because we know very well that across the peak of resonance, there are large variations in the frequency of the function. And that is especially true when we are characterizing a system with very low value of damping ratio. Okay. Then, when looking at the columns now, this vision is for the row up to now, but now when we are looking to the columns, then we can consider in your iteration process only those columns that are truly participating in the formation of the rank of your sensitivity matrix. Okay, that means that we are retaining all the P design parameters that are contributing to the solution that we are looking for. That means that maybe the other components of your P vector or non-P vector are already found out. So there's nothing to do more about those components. So we remove those components from the solution scheme at the iteration point. Okay, so only columns that do participate to the rank of the sensitivity matrix S are retained in the analysis. Okay, by the way, this is checked by introducing the singular value decomposition, SVD, of your sensitivity matrix. Okay? So that's what we can have in evaluating the check. Okay, so the rank of your system. So is done the decomposition of your sensitivity matrix as let's say the left eigenvector times the diagonal matrix of the singular values, and then the right eigenvectors of the singular vectors. Okay, this diagonal matrix of the singular values is a matrix of positive values, sigma 1, sigma 2, up to the dimensions. For example, that one is sigma I square r co-singular values, and are always positive. Okay, by counting the number of sigma by square that are larger than a prescribed small quantity, we have the information about the rank of the sensitivity matrix. Okay, so this number of non-zero values of the singular values is the rank of your S. Of course, this is an estimate once again because you have to define prescribed small quantity. Okay, so it's up to you. If you choose a very, very small quantity, then maybe you are also considering that the noise is contributing rank of S. If you are considering a quite large value of these small quantities, then only the most important rows, the columns are considered in the formation of the mark. So it is just a trade-off of this discussion. Okay, so that's it with the structure updating method. We considered the error matrix method yesterday. Then we start the predictor corrector method, and then today we end this description of the predictor corrector method just by discussing a possible solution sequence, the iterative procedure, and some let's say remarks on how you can use this approach in order to solve for the unknown quantities that once again are the design parameters for the update. Please consider that on top of that, there is the crucial choice of the design parameter. So let me write that. So the choice of your PI is crucial, as we already discussed. And that is the difficult task that the engineer has to face, because a wrong choice of the design parameters for updating means that you can't update your final element model. You just maybe change the point of view, and then you have a very nice, refined numerical model whose structural dynamics is the one that we are measuring, we are estimating in our laboratory test activities. Okay, questions on that? You have any doubts? You feel that there is something to review? Okay, if not, please consider that there are lots of activities, there were lots of activities and still are running some activities for the master degree thesis in this topic. You can use all the stuff or the instruments that we have in the laboratory, and therefore you can think about of the structure updating problems as your final degree thesis topic for your master study. Okay, so if you wish to go into more details, just let me know, email me so that we can arrange a meet and then we can discuss what could be a possible activities for your thesis. Okay, now let's change the topic and let's consider an innovative approach that has been into the scientific literature by let's say no more than 2 decades now, and that is the operational model analysis. Oh. Generally referred to OMA. And this operational model analysis has the main objective to estimate model parameters without the information of the input excitation. If you remember, when you consider whatever estimating technique for the model parameters, single degree of freedom, multi degree of freedom, time domain, frequency domain based approaches, all of these methods are referring to the as starting point mainly to the frequency response function. That is, we have to carry out a test in which we measure both the input, that is your dynamic loading, and your output, that is your acceleration response in some points. Okay, according to your MIMO or SIMO analysis, you can have different configurations. Okay, but however, you have to measure both the input and the output, and by knowing that, using the estimating technique, that we know, let's say H1 and H2, you are able to have your FRF matrix, and therefore using whatever other estimating technique you can estimate your model parameters. Within this method, with this idea of the operational model analysis, model parameters are estimated from the output responses only. Okay, that is no input measurement are needed. Okay, and that is one of the best feature that these methods are having. Can you see why? Let's, for example, think about a civil engineer structure, a large building, or a long-haul bridge. Okay, therefore, if you want to characterize those structure from the model parameters point of view, you need an excitation. Can you figure out how large, how big could be a model hammer to excite an entire building or an entire bridge? Okay, it is practically impossible. Okay, so instead, if you use, for example, the wind excitation, if you use the traffic from the cars, from the trucks that are passing through the bridge as a mean of dynamic excitation, then you can have your output responses that could be used to the estimate for your model parameters. But for our analysis, for our purposes, can you figure out the power of these approaches when you are referring, for example, to flight tests? Okay, if you would like to identify, for example, the root locus of a flight aircraft at different flight speed or whatever flight dynamic pressures, then you are not required within these approaches to measure any input at all, but just from the output measurement, that is from the measurement of the output acceleration, for example, you can estimate the model parameters in terms of natural frequencies, damping ratio, and mode shape. That could be impossible using the other approaches that we saw together during the last week because we can't measure the okay. But also you can extend that these approaches to the use, therefore to the estimate of, let's say, whatever operating structure, let's say windmills, let's say for wind energy, for example, or ships, cruising ships, okay, for which the, let's say, the sea turbulence is exciting your ship, or your engine is exciting your ship, and therefore you can, from the output response, you can measure, you can estimate your model parameters. That could be really impossible to estimate without these approaches. Okay, so let me just mark that for flying aircraft. For space vehicles, civil engineering structures, okay, wind energy, therefore ships, so naval engineers, okay, and therefore whatever other application in which we are operating systems. Okay, just because no input measurement is needed. Now, today I'm going to show you two approaches. Okay, these approaches, there are many techniques. Okay, so there are many and OMA techniques available. We will see just one in the time domain and another one in the frequency domain. Okay, so let's have these two techniques. The first technique that we are going to see is called balance realization method, and this operating in the time domain. So let me call that balance realization method. That is generally referred to BRM. Okay. Whereas the other approach, the frequency domain, is called frequency domain decomposition. Okay. also known as FDD method. Okay. By the way, this approach, the balance realization method, okay, belongs to the so-called SSI techniques, more general techniques. Okay, SSI means stochastic subspace identification techniques. Okay, so let's start with that. So let me consider the estimate of the modal parameters in the time domain with the technique that is balance realization method. Okay, and within this approach, your system time domain evolution is described. So the system evolution is described by the very well-known equation x at time instant k plus is equal to a x at time instant k plus your whatever noise, okay, and your output yk, okay, is that you observe at the time instant k is giving you by the response matrix C times your xk plus whatever noise. Okay, so that is your basic equation. Please note that A is your state matrix. Okay, dimension is n times n. If your state vector x has dimension n, okay, k is the kth time index, okay, y k vector is the response, system response, okay, that are defined over n rest points, okay. C is the response matrix, okay, dimension is n rest times dimension of the vector, and then your wk and vk vectors is the noise, okay, the input and output stage, respectively, okay, having 0 value by assumption. Okay, stochastic and whatever. Okay. Okay, before we go on, just to be sure that the k-time index, okay, is telling me that is delta t is your sampling time, then okay, sampling time, then multiplying that by k index, you have the information of the instant time tk, okay, and therefore your state vector at the time tk is what I wrote there as xk, okay, and therefore for the response system yk, okay. So is the response system uptime instant time k is by definition your yk vector, okay. So let's stop for 5 minutes, more than that. So let's resume the class by 3:10. Okay, and then we keep going. Questions?
Excuse me, Professor.
Yes.
In the singular value decomposition, the matrices U and V, what
Yes.
are?
Are the singular vector left and right singular vector matrices.
Okay.
Okay.
It's a decomposition of a matrix into these three.
Yes.
Okay.
Yes. Yes. It is a quite common matrix decomposition. The most important fact of that decomposition is that you are having a diagonal matrix of the singular values, and these singular values, and that is the important factor of this transformation, are all positive. Okay, that is why we are using the notation sigma square, because those values are all positive values. And just by comparing the different order of magnitudes of these singular values, you can say what is or what are the most important contribution, for example, to the rank of those of the matrix that has been transformed using the singular value composition. Okay.
Okay. Thank you.
You're welcome.
What's good, Love Life crew? It's your boy Musa back with another Bollywood reaction. Priyanka. Let's go. Priyanka. Why she crying? Who are you looking at? Oh, Chai. So you got Deepika and Priyanka.
Okay, let's recap the class. So in the balance realization method for the operational model analysis, that is for the estimate of model parameters without the measurement of the input excitation, the starting point is the state space formulation, as you know, and the equations, that is the system evolution, are here reported in the screen that you can see right now. Okay, then we define the quantities. And just one last remark on the noise, because W and V are the noise on the input and the output stage, respectively, having zero mean value, we can also think to avoid this contribution. Okay, so these contributions are neglected, just because they are white noise. So in our equations that we are going to write right now, their contribution could be considered as negligible with respect to the other ones. So remember, the state space matrix A, okay, gives the model parameters. Remember, when we consider the Ibrahim time domain technique, we saw this point in detail. Remember, we saw that your state space matrix A could be decomposed as your modal matrix, complex modal matrix, times your diagonal matrix of the eigenvalues, and then the modal matrix transpose, okay? From the lambda, capital lambda, we are having the damping, decay, the natural frequencies, and then the mode shapes, okay? Actually, the phi modal matrix is referring to the whatever state vector. We are only available the measure, okay, degrees of freedom from the output measurement. So your psi R mode could be obtained from the C matrix and by considering the previous identified eigenvalue, okay, of your matrix A. Remember, so the matrix C, that is your response matrix, is used to have an estimate of your mode shapes and the measure degrees of freedom. So that is mode shape R defined over the measure degrees of freedom, and that is the mode shape R, once again, defined over the state vector. So that's the reason why you need a C matrix. Okay, so the method, the balance realization method, okay, identifies your state matrix A and your C matrix of the responses. Okay, once you know this, then you solve the problem. So let's see how we can estimate those matrices, the state space matrix A and the measure of the response matrix C. Sorry. Okay. We are having all the output responses. So from the output response measures, okay, and these are your y, k, okay, we can, the correlation function let me call these R K correlation function, okay, are defined, are evaluated. This correlation function means that it is the correlation function on the all output responses evaluated at time tk. Okay, with these correlation function matrices, we can build what it is called the Hankel matrix of order P and Q. Let me see then the Hankel matrix H of order P and Q is an Hankel matrix shapes whose elements are the correlation function of time instant 1, and correlation function time instant 2, correlation function time instant 3, okay, up to the correlation function time instant 2. Then what we got, correlation function time instant 2, and then up to the last one, correlation function time instant p. Then we got correlation function p plus 1 till the very end, that is your correlation function p plus q negative 1. Okay, so we built the Hankel matrix okay, of order p and q. Dimensions are, of course, p times the number of responses for the number of row times q times the number of responses as number of columns. Okay. Sorry, reference point. Sorry, I did that. Being, of course, the correlation function of order whatever k, just to be general, k with dimension and rest times and ref. And the reference number is the number of points that we consider for reference. For example, if you are evaluating the vertical bending of a flying wing, that maybe you can have just 1 degree of freedom, that is your reference channel, for example, the wing tip channel. Maybe you can have 2 reference channels that are measuring the vertical acceleration, that is, one is at the leading edge, the other one is at trailing edge, so you got 2. Maybe you can add two or more at the midsection of the wing, and so far and so on. Or if you are considering the whole 3D behavior, such a dynamic behavior of the wing, therefore maybe you can consider also additional reference channel that has to be considered a reference because you are evaluating your correlation function considering those channels. Okay. That is a starting point. So the Hankel matrix is a known quantity. It is up to you to define what are P and Q. So P and Q are arbitrarily defined. Sì? Yes?
Potrebbe ripetere che cosa sono i reference point? Non ho capito.
Reference point are those measuring channels that you consider to build your correlation functions, and so you have to consider two channels, okay, in order to build a correlation function. Those reference points, reference channels, are defined upon the most important channels in your measurement. For example, if you are considering a flying wing, you are considering the vertical bending of such a flying wing, maybe you can have one reference channel that is the output acceleration on the one point at the wing tip. If you would like to consider also torsion, that maybe you can have two channels at the wing tip, one at the leading edge and the other one at the trailing edge. If you would like to have a more refined analysis, maybe you can introduce additional points, is the wing midsection channels. So the number of reference channel is increasing according to what is your task, according to what is your accuracy demand. If you consider, for example, the whole 3D structural dynamic behavior of the wing, then you have also to consider other channels in the X and Y direction, so in the other two directions. Okay, but however, it's up to you the definition of these reference channels. For sure, there should be some channels that are characterized by low noise and are characterized by that are significant for your response. Okay. So, because you know these time responses, you can build your HPQ matrix, that is the Hankel matrix of the PQ. By the way, the order PQ is completely arbitrary. We will see later on some rule of thumb in order to choose your P and Q, but however, they are arbitrary. Then the process, consider that the Hankel matrix HPQ could be factorized as product of two matrices. Let me call it OP times CQ. Okay, and the OP matrix is your observability matrix of order P. Okay, it is a real matrix. Okay, dimensions P number of responses times the dimension of your state. Okay, and the CQ matrix is your controllability matrix of order Q, and once again it is a real matrix. Dimension state of the system times Q times number of reference channels. Okay, please note that this information should be available to you when you follow the Professor Battilotti course. I know now that you are becoming emotional about that. Your teardrops are becoming important, so please wipe your tears because of this equation. But however, it is very important. Moreover, it is possible, I'm not going to do that, it is possible to show that your observability matrix of order P could be written in this way. So your C matrix, then C, sorry, C times A up to the last one, C times A to the power of P negative 1. And your controllability matrix, CQ, could be written as your G matrix, then A G matrix up to the last submatrix A to the power of Q negative 1 times G. Okay, in which your G matrix is the expectation matrix, is a correlation function between your response, so between your state at the K plus 1 time instant and your response at the K time instant. Okay, so this is a correlation between the two. So you are done. Please note that, moreover, the rank of your observability matrix of order P is equal to the rank of your controllability matrix of order Q. Okay, and it is equal to twice the number of modes. Okay, model order. Okay, so it is very nice for you to have this information. So it is just a matter of decomposing your Hankel matrix of order PQ into these two matrices, O and C. Once we got your O matrix, you can have your C, and therefore you can have your A, and therefore you are done. You have solved the problem. Now the question is, how can we solve for that? Please remember the singular value decomposition. So the singular value decomposition applied to the Hankel matrix could be written as SVG, singular value decomposition, applied to the Hankel matrix of order PQ. Okay, could be rewritten as your U left singular vectors times U2 right singular vector times the singular value sigma 1 sigma 2 0 0 times your right singular vector V1 transpose and then V2 transpose. Okay, we can also rewrite that as your U1 sigma 1 U1 transpose plus U2 sigma 2 V2 transpose. Okay, please note that this could be a complex, a whole full complex matrix in general. Okay, and they are, and these matrices, of course, are having the eigenvalue and eigenvector because they are in the Hankel matrix as we already defined. Now, if, and that is the critical part of this approach, if we define this sigma 1 matrix as the diagonal matrix of those singular values, sigma 1 square, sigma 2 square, up to sigma n square. Okay, so that your sigma 1 square is larger than sigma 2 square, that is larger than the last one, and they are of course all positive quantity. And we define sigma 2 diagonal matrix as composed by the terms sigma n plus 1 square, sigma n plus 2 square, up to the last one, sigma square p and response. Okay, so that once again sigma n plus 1 square is larger to all the other ones until the last one p and response, and all of course are positive quantity. Okay, now if those two matrices could be recast so that we are just retaining the most important components, okay, if such an n is chosen so that, let's say, sigma n plus 1 square over sigma n is, let's say, greater than 0.01, that is 1 order of magnitude, then we find out the system n is the system order. Okay, and your sigma 2 matrices could be neglected because is not contributing to the system information. That's because the singular values are very, very low if compared to their one. And therefore, at the very end, what we can say is that the Hankel matrix of order P and Q could be rewritten as U1 less singular vectors times sigma 1, that is the diagonal matrix of the most important singular values, times P1 transpose matrix. Okay, and therefore an estimate of the observability matrix is given just by OP, observability matrix, is practically equal to the U1 sigma 1 root square. Okay, and you are done. Can you see that? Because you have just to build your Hankel matrix, and that is very easy. Perform the singular value decomposition. In MATLAB, it is very easy indeed. Then you have just to define a criteria. What eigenvalues order of magnitude do you want to retain in your analysis? Okay, for example, a difference in a 1 order of magnitude. And therefore, the observability matrix could be obtained just by that. Okay. So your controllability matrix could be obtained from the first, by definition, and rest rows of your observability matrix of order P. Okay, A from a least square solution. Okay, from the other two set of n rest rows of your OP, okay? That is your OP north is equal to C, that we already know, times E, okay? And these are the second set of and rest rows, okay? That is a shift to the north of the observability matrix of order B, okay? And then you are done. You can have these solutions, okay? Generally speaking, we are choosing your number of P and Q. Remember, I told you that we have a degree of uncertainty on doing that. We can choose whatever, but generally we choose P and Q so that we can have a large number of data that we can use for the solution sequence, and therefore the least square approach could be quite robust and give an accurate solution. However, because we are not sure about this value, generally speaking, we are introducing another stabilization diagram by changing the order of P. Sometimes what we are having is that the P value, the Q are, let's say, and P are connected one each other. So sometimes P is an alpha value of Q, alpha integer number. Okay, and therefore the polar parameters are estimated by using the stabilization diagram that we already considered. Obtained by varying P. Okay, so we increase P, we have a different and increasing size of your Hankel matrix. We perform the singular by decomposition. We retain only the parts that we are considering important in terms of singular values. And then what we are doing is just solving here it is. Okay, C from the first and response rows of P, and then a least square solution of that equation that we are seeing in the display right now. Okay, then from the knowledge of A, then you have the eigenvectors, then you have the eigenvalues, and then you put in the simplification diagram, and then increase your P value and do that again until you find that those values, those responses, sorry, those natural frequencies and ratios are not changing at all by increasing the order, by increasing P, and therefore you are done. Okay, very good.
Professore,
Prego, questions?
sì, quando ha definito un attimo solo il system order n, nell'ipotesi, insomma, per l'approssimazione, è sigma n più 1 al quadrato diviso sigma n al quadrato maggiore o minore di 0.1?
Maggiore?
Eccolo qui.
Maggiore?
Maggiore? Ok.
Yes, because we are saying that the most important components, the most important singular values are those that are larger of one order of magnitude with respect to the lower one. Okay, so
Okay.
and the system order is the one that is characterized by the most important singular values, or sigma n square, of course.
Ok, va bene, grazie.
Okay. So as you can see, it is very interesting, and it is use this approach many times when referring to flight tests that I have the chance to work with when doing some, let's say, Flutter certifications activities. Okay. Now, let's see the second approach. The second approach is the frequency domain decomposition, FDD method. Okay. Oops. Okay. And this approach, once again, starts from the output measurements. Okay. Let's assume to have the output measurements as your, let's say, x1 of time. Sorry. X2 up to xn bn, the number of degrees of freedom, okay, that we are having, number of output responses in general. With that, we can build our power spectral density matrix of the output. Let me call that Gxx of omega. And that is equal to Gx1 x1 of x1 omega G x1 x2 of omega, and then we get G x1 xn of omega, and then till the last one, rho xn x1 of omega Gxn xn of omega. Okay, so that is your output power spectral density matrix. That is, of course, a power spectral density function for each element, and these are defined over the whole number of degrees of freedom. Just one sec that I'm going to plug in the charger. My tablet. Okay. Here we go. Now, because of that, you can refer to the element of this matrix Ij is the power spectral density between the degree of freedom I and G. Okay. Now, for a linear dynamic system, remember, we can, so for a linear dynamic system, we can refer the output power spectral density matrix with the input power spectral density matrix by using the frequency response function. Okay, so we can say that your Gxx of omega is linked to the GFF of omega, that is your power spectral density matrix of the input, okay, through the information of the frequency response function. Here is complex and conjugate, and there H of omega. Here is the transpose. So this is just complex and conjugate, and it is transpose operation. Okay, and because of that, we can assume now that if, and that is the main hypothesis, if the input, oops, is white noise, that is stochastic with zero mean value, then we can say that your GFF, that is your power spectral density matrix evaluated between all the possible input, is a constant matrix. Oh, sorry. Well, okay. A constant matrix that could be set into a form, let's say, an F times an identity matrix. Okay, that is, we are having a diagonal matrix. That is, there is no correlation in the space and domain between different input excitation, and because we are having just one value, we are having a frequency. What we are having is that we are also having a constant spectra. There is no dependence in the frequency domain. So that means that it is the input is constant in time and space by writing that equation. Okay, if that is true, what I can say is that your frequency response function matrix H, that remember is written in terms of your residual terms, K goes from 1 to the number of moles. Remember your A matrix K over J omega negative lambda K plus the constant conjugate part, A constant conjugate K J omega negative lambda K constant conjugate part. Okay, just by saving you a lot of equations, we can write that your GXX, your power spectral density matrix of the output, could be rewritten as summation for all the modes 1 to m, your EK times psi K, that is your vector, psi K transpose divided by J omega negative lambda K plus the complex and conjugate part psi K complex psi K emission divided by the pole complex and conjugate pole lambda K complex and conjugate. Okay, so after some, let's say, algebra that I'm skipping, okay, now if we consider omega equal to the half natural frequency What happening to that equation? We can say that the Gxx of omega and R, that is the power spectrum density matrix evaluated at the natural frequency of the system, could be rewritten as dr times your psi r mode transpose divided by j omega and r, okay, negative lambda r plus er constant conjugate psi r constant conjugate psi r emission divided by j omega n r negative lambda r constant conjugate. That's not it. Plus all the remaining parts. Okay, so plus the summation sign that from k that goes from 1 to the number of moles, but with k different with respect to the r index of the same quantity. The k psi r transpose divided by j omega n r negative lambda r plus the k, oh sorry, k not r. Okay, psi k and here is your k, yes, plus the k constant conjugate, the numerators the same, conjugate psi k emission divided by j omega n r negative lambda k. Okay, but if we are under a single degree of freedom system hypothesis, that is at the resonance condition, just the mode that we are considering, just the natural mode that we are considering is important to the response, and that equation, that hypothesis is most of the time a good one, then this term could be considered as higher order term. Okay, if the response is dominated by the R mode at the R natural frequency. Okay, and that is practically always. Okay, this is a first result. The FDD method is not over yet, because now if we consider that the singular value decomposition of your Gxx matrix evaluated for each omega, okay, could be rewritten as your U sigma and B transpose when omega is equal to your R natural frequencies. Okay, it follows that the rank of your Gxx matrix when omega is equal to the R natural frequency is practically 1 by hypothesis. Okay, and therefore your your GXX matrix at the natural related at the natural frequency could be rewritten as your left singular vector, let me say corresponding to the nth singular value, and then your Hermitian, okay? Because we are having let's say causal system, what we can say is the left singular vector matrix is equal to the composite conjugate V matrix, okay? And therefore what we are having is SVG of G XX is equal to U sigma U Hermitian, okay? Because physical system. Okay, so we end up with this other expression. Okay, generally the SVD, so the singular value decomposition algorithms are ordering your singular values from the larger to the lowest amplitude. Okay, so generally what we are having that is M index is equal to 1, is set equal to 1 by numerical routines. Okay, and therefore you have a valuable tool to estimate your model parameters. While doing that, you can, for example, track the evolution of the singular values frequency by frequency. And when you are approaching one of the natural frequency of the system, because of our hypothesis, because of the singular degree of freedom hypothesis, what we are having is that at that frequency, only just one singular value will survive. The others will be zero, theoretical, will be very, very low in practical cases. And therefore, what we can say is that just by tracking the singular values, when we are at the frequencies which correspond the highest value, the singular value, then we have found the natural frequency. Because of the equation that I marked with green, we can also an estimate of the eigenvector from the corresponding singular vector, okay? And then we are done. So natural frequency from the singular value plot, and this plot is of the shape. We have a y-axis, which we are putting all the sigma i's, in the x-axis your frequency. We will have many singular values here, and then at a certain point what we are having is just one singular value that is going high, and so far so, and the others are all very, very low. At the frequency in which we are having the first maximum singular value, we have the natural frequency, estimate of the natural frequency. Here we got natural frequency 2 at the second sigma I square maximum. Okay, and the corresponding eigenvectors, so eigenvectors the singular vector corresponding to the local maximum singular value. Finally, so eigenvectors, natural frequency, the damping ratio, that is the last parameter, damping ratio from the logarithmic decrement technique applied to the inverse Fourier plus Fourier transform of your gxx of omega evaluated across the just identified omega and r. Okay, in that case, what we are saying is that the system is behaving as a single degree of freedom system, and therefore the inverse Fourier transform that is the proportional to impulse response is a single degree of freedom response, and therefore you can easily use the logarithmic decrement technique to find out the value of the damping. And therefore you have all the parameters, natural frequency from the maximum value of the singular value, most shapes, eigenvectors from the corresponding singular vector, and finally the damping ratio by anti-Fourier transform, inverse Fourier transform, so going back in time domain, in the frequency range just across the just identified natural frequency of your power spectral density. And therefore we have the correlation function that is a single degree freedom system, and then the logarithmic decrement. This frequency domain decomposition method is based once again in a random stochastic excitation, white noise input excitation, because otherwise we can't do that much. Of course, there are some, let's say, improvements to this method by taking into account other factors, but it works very well. And once again, this operational model analysis called frequency domain decomposition has been used many times. I use it many times in flight tests for flutter certification in order to track, for example, the damping ratio over 12 dB G plot that is typical in the flutter characterization using the flight tests. Okay, and once again, as we got some degree thesis activity in the structural updating, we also have some degree thesis activities in this novel operational model analysis method applied to whatever flying structure, could be space, could be aeronautical. So everything that is flying for flying tests could be used to estimate the model parameters in the frame of the operational model analysis. Okay, that's it for today. I hope that you enjoyed the class and these novel methods. See you on Friday for the last class of the semester for the course. Okay. Thank you. Thank you very much. Questions, of course, I'm here. Okay. If there are no questions, thank you very much all, and see you on Friday.